Azimuth. The definition of the azimuth is something like this. The azimuth of a line is the horizontal angle measured from a specific meridian, usually north, to the line in clockwise direction. So let's see what that means. If I take a line AB, just any line, let's say this is A and this is B, and the definition says it's from a specific meridian, usually north, and I will draw my north meridian. So this is north, and the azimuth angle is the angle starting from that meridian clockwise to the line. And let's call this angle theta. So the azimuth of line AB is equal to theta. Pretty easy so far, right? And now let's see what is the azimuth of BA. So if I go here and I draw the meridian, north meridian, again, this is north. It's a little bit crooked, but that's fine. You pretend this is a straight line. Okay, this is the north meridian. And the definition says that the azimuth is the angle measured clockwise. So we have to go in this direction. So there you go. This is the azimuth of line BA. And I want to just go ahead and think a little bit. If I was to extend our line a little bit more, so if I'm extending, I am getting that this is actually our angle theta, correct? That's right. And then, which means I'm left with another, this angle, which is 180-degree angle. We know that, right? A straight line, this angle is 180 degree. So this makes that the azimuth of BA is equal to theta plus 180 degrees. So let me write this way. So the azimuth of BA equals to the azimuth of AB plus 180 degrees. So what this points out is that if you know the azimuth of AB, you can calculate the azimuth of BA. And this is 180 plus theta. Okay, pretty straightforward. I think this is easy to understand what azimuths are. Moving forward, bearings. Definition of bearings sounds like this. Bearings of lines are directional horizontal angles with respect to a meridian, north or south, measured at the originating point on the line. Okay, let's see what that means. If I'm giving a bearing of a line, I'm told that it's south 30 west, 30 degrees west. Let's see what that means. So I'm told that the meridians here are north or south. So I'm giving the bearing south. So my meridian is going to be south. Okay, this is the south. And I'm starting here, and I have to go southwest. I know that if this is north, south, west, east, maybe I should explain it this way. Okay, and if I was to draw the coordinate system, right, north, south, west, east, I have southwest, which tells me that I am in this quadrant over here, and my line is south 30 west. So I draw a line starting from here, 30 degree with respect to the south meridian. So this is 30 degrees. And this is my line A, B, let's say. And now this is how you draw a line, knowing the bearing of that line. Let's take another bearing. Let's say I have north 37 east. Right away, you can look at this coordinate system and you know you're going to be situated in this first quadrant. And you have to draw that line with respect to the north meridian. So you're going to go north, east, 37 degrees with respect to the north meridian. And this is, let's say, AC. This is your line AC. So this is how you draw lines when you know the bearings of the lines. Now, moving forward, let's talk about deflection angle. The definition of deflection angle is an angle measured to a line from the extension of the preceding line. So let's see what that means. Let's say you're giving line AB, and now let's say you're giving that this line has the azimuth of 45 degrees. So let's say azimuth of AB equals to 45 degrees. And now the next line, BC, you're giving that the deflection angle, right? Deflection angle is equal to, let's say, 30 degrees to the right. You're always going to be giving deflection angle a certain degrees to the right or to the left. And now let's see, how do we represent that? In order to understand, so this is the point B where this AB line ends. And in order to be able to draw the next line, imagine that you're standing on this line and you're looking forward. I'm going to extend line AB. And if you're looking in this direction, right, this is your right hand right here, and this is your left hand, right? And now we are told that we have to, BC has a deflection angle of 30 degrees to the right. That means that from this line, from the preceding line, as we're told in the definition, right, from this line, I have to deflect 30 degrees to the right. So I'm going to deflect in this direction. So the line BC go all the way, and this is 30 degrees. So this is my deflection angle. And this is how I use deflection angle to represent the next line. It's a little bit messy here. So again, you stand here at the end of your line. And if you look straight ahead in this direction, this is your right hand, this is your left hand, and the deflection angle you're told is 30 degrees to the right. So from this line, which is in the definition preceding line, you go 30 degrees to the right, based on your right and left hand if you look forward. And this is how you use the deflection angle, or represent the deflection angle. Now let's move forward. Let's talk about latitude and departure. The definition says, in the rectangular coordinate system where the north-south meridian serves as the y-axis and the east-west line serves as the x-axis, the projections of a line are termed latitude, which is a y projection, and departure, which is a x projection. So let's go ahead and draw the coordinate system based on what we're told in this definition. So we have north, south, west, east. And as the definition tells us, north, south, we know it as y-axis, and west, east, we know it as x-axis. I'm just going to put it here to make it easier for you to visualize. And let's say we have a line AB. We have a line AB here. A, B. And definition says that the latitude and departures are nothing else than the projections of this line on X and Y axis or north, south, west, east. So this distance, it's departure. It's called departure. And then the vertical distance, let me see how I'm gonna, over here. This distance, the Y projection, it's called latitude. And another important thing to mention here, and I'll go to the FE Handbook, and I want to mention that FE Handbook, or in the FE Handbook, we don't have a surveying chapter. Everything that is surveying related is found in the transportation chapter. So you can either go straight to transportation, or I'll just go ahead and search for latitude. I already had that type. But if you are anywhere else in the FE Handbook, right, and you just type latitude, it's going to get you straight to this page where you can find the coordinate system with the latitude and departure shown. This is north, and this is south, this is west, and this is east. So what is to mention here is that north latitude is positive, east departure is positive, west departure is negative, and south latitude is negative. So why is this important? If I go back to my problem here, right, this south was negative, and west is negative, north is positive, and east is also positive. So for my line here, I have departure negative, because west is negative based on FE Handbook, right? And latitude is also negative. Let's say you are giving the bearing of a line as south 45 east, and let's represent that line. Southeast, I'm going to be in this quadrant here, and I'm going to draw the 45 degrees with respect to the south meridian, and this is 45. Okay, and now the latitude is vertical, so the latitude of this line is going to be negative because south latitude is negative, so I'm going to get minus latitude, and the departure east departure is positive, so I'm going to have a positive departure. Okay, I hope this makes sense. The only thing you just have to know is that latitude and departures are distances, and they are projections of your line on the north-south or y-axis and west-east or x-axis. Moving forward, let's talk about northing and easting. And this is pretty easy to talk about once we have discussed latitude and departure, because northing and easting, based on the definition, let's just read the definition quickly. Whereas latitude and departures are north-south and east-west projections, respectively, of a line segment, northing and easting are coordinates of points in a traverse. So if we're giving a line AB, northing and easting are the coordinates of this line. And you will understand more once we solve a few examples. So let's go ahead and do that. A closed traverse ABCD is shown below. Which of the following statements is incorrect? So pay attention to that. We are asked which one is incorrect. A, there's a typo here. The bearing of line AD is south 23 degrees east. So let's locate line AD. Here is A and here is D. So this is our line, and we're told that the bearing of line AD is south 23 east. Based on the definitions we have discussed before, we know that the bearing is drawn to respect to south or north meridian. In our case, we're given south. So this is our south meridian, and it is southeast. So we're going to be, east is in this direction, right? So this is our quadrant. And we are told, we know that this is 67 degrees, which means that this angle is as well 67 degrees, and which leaves us with this angle being 23 by subtracting 90, or 67 out of 90. This is 23 degrees. So indeed, based on our drawing here, AD has a bearing of south 23 east. So this statement is correct. We have to look for the incorrect one. Let's go to B. The azimuth of line BC is 73 degrees. Let's locate line BC, B, and C. So this is line BC. And the azimuth, if you remember from the definition, is drawn from a meridian, from a north meridian, and the angle is drawn clockwise to the line. So we're told, based on B, that this angle should be 73 degrees. And now it's very easy here to see that this is not true, because this angle is 90. And then here we have, so this angle has to be greater than 90 degrees, which is not true. So second statement B, it seems that is the incorrect one. Let's just move forward and work on all of them just to learn a little bit more. So C says that the latitude of line AD is negative. So let's go back to line AD and find the latitude of that line. And I'll, if you remember, or let me go back to the FE Handbook, where line AD is, the bearing of line AD is south 23 east. So going back to this FE Handbook, southeast is in this quadrant over here. And we know that the latitude in that quadrant is negative. So C says the latitude of line AD is negative, and this is correct. Indeed, the sum of the latitudes for all four lines is equal to the sum of all departures. And this is something we have not discussed, and it's not given to you in the FE Handbook, but I need you to learn that the sum of all the latitudes in a closed traverse, as the one we have here, is equal to 0, and the sum of all departures in a closed traverse, as the one we have, is equal to 0. So this is something very important to remember, that the sum of departures equals to the sum of the latitudes and equals to 0 in a closed traverse. So this is also correct. So the correct answer here is B. The azimuth of line BC is not 73 degrees. Now let's work on our next example. The table below describes a traverse ABCDE. Determine the interior angle at C. So we're given this table with some information about the ABCDE traverse. But first, I would like to talk to you about how to transform these angles that have minutes and seconds into degrees. So we know that 1 degree is equal to 1 hour, and then 1 hour is equal to 60 minutes, and 1 hour is also equal to 3600 seconds. So if we are to take this angle 132 degrees, 23 minutes, and 45 seconds, this will equal to 132 degrees plus, and we would take the minutes and divide them by 60 to achieve degrees, plus 45 seconds, and we would divide them by 3600 seconds in an hour. Okay, so now the only thing you got to do, just use your calculator and find out how much this is. So 45, 3600 divided, 2360 divided, we add that up, and then 132 degrees plus, and I'm getting 132.395. I'll round it up to 132.4 degrees. Okay, so this is 132.4 degrees. Let's go ahead and also transform this deflection, and this is deflection angle. Somehow it was left out. Okay, let's calculate this deflection angle. We have 52 degrees and 34 minutes, and this will equal to 52 degrees plus 34 minutes divided by 60 minutes in an hour. Okay, let's see how much is that. 34, 60 divided 52 degrees plus, I get 52.5666, so I will round it up like this, 52.57 degrees. Okay, let me write down here 52.57. All right, and also let's go ahead and calculate this one. I will write it on this lower page here. I'll scroll down a little bit. So I'll have 137 degrees, 46 minutes, 32 seconds. And this is going to be 137 degrees plus 46 minutes divided by 60 minutes in an hour plus 32 seconds. Going to divide by 36 seconds in an hour. Now let's see, what do we get here? 3600 divided 46, 60 divided. We add that up, and then adding 137. So this angle is going to be equal to 137.775. I'll just do 78, round it up like that. Okay, so this is 137.78 degrees. Okay, we also have DE. Let's go ahead and do DE as well. 96 degrees, 56 minutes, 22 seconds. And this is a good exercise for you to do if you didn't know how to transform minutes and seconds into degrees. This is actually a good exercise for you to do. So again, this is 96 degrees. Plus 56 minutes divided by 60 plus 22 seconds divided by 3600. And let's see how much are we getting here. 3600 divided 56, 60 divided. We add this up, and 96 plus. So the angle I'm getting is 96.94. Round it up. Okay, so this is 96.94 degrees. Okay, now let's go back up here. Once this is done, let's go ahead and start by representing the line AB. So the line AB, we know the azimuths, and the azimuth is 132.40. Okay, so we're starting at north. We know this is 90 degrees, 132.40 is going to be looking something like this. This is A, and this is B. So far, so good. And the length is 271.12 meters. Now, let's go ahead and represent BC. For BC, we're not given an azimuth, but we're given the deflection angle. And we've learned previously how to represent or how to use the deflection angle to represent our line. I'm going to go ahead and place myself here and elongate my line a little bit. So I am looking forward. I'm looking in this direction. And if I'm looking in this direction, it means that this is my right hand, right? And this is my left hand. So now the deflection angle is 52.57 left. So from this line, I'm going to deflect 52.57 towards the left. So this is the angle, 52.57 in the left direction. Okay, and my line is 28918 BC. This is BC. Great. And now for CD, I have the azimuth, which is 137.78. So I can go ahead and represent CD by starting from the north meridian again. Okay, place it at C. And the angle is 137, so this is 90. Go a little bit below that. It's okay if you're not exact. You have to approximate anyway. So this is CD. Okay, so the azimuth for CD, we know it is 137.78. The azimuth for AB is 132.40 degrees. Okay, and we are asked to determine the interior angle at C. So this is what we have to calculate. Angle C, or BCD. Okay, let's see how can we do that. So in order for me to calculate C, it would be helpful to know this entire angle, right? Now, this entire angle, if you notice, this is the azimuth of line CB. So the azimuth of line CB is equal to the azimuth of BC plus 180 degrees. Okay, so do we know the azimuth of BC? I don't think we know it, but I know we can calculate it. This is the north meridian. The azimuth of BC is this angle right here. Okay, so how can we calculate the azimuth of BC? I'm looking at the azimuth of AB. So we have the azimuth of AB, and we also have the deflection angle. And looking at this, this is the azimuth of AB. This angle right here is 132.40 as well, right? Because this is north, and this is the extended line. So this is in orange, is the azimuth of AB. Or maybe I should do a better job if I just keep it in green so everything makes sense. So this is also the same angle. It's as this one over here. It's just a little bit bigger because I don't know how to squeeze it there. Maybe I could have done it here. Anyway, and in order to calculate the azimuth of BC, we just take the azimuth of AB and subtract the deflection angle. Does that make sense? Let's go ahead and do that. So the azimuth of BC is going to be equal to the azimuth of AB minus 52.57 degrees. And this equals to 132.40 degrees minus 52.57 degrees. And this gives me the azimuth of BC equal to, go ahead, take your calculators and calculate with me 132.40, 52.57 minus, and I get 79.83. 79.83 degrees. Great. So now we know that this in purple, go ahead and get back my purple, is 79.83 degrees. Great. So now that we know the azimuth of BC, we can calculate the azimuth of CB. We can come back here, right, and take the azimuth of BC, which is 79.83 plus 180. And I'm kind of squeezed over here. So I'm going to go back down here. Azimuth of CB is equal. So from here, I went straight back here. Azimuth of CB, use your calculators, 180 plus, I get 259.83 degrees. Perfect. So now we know this purple angle, right? This whole angle, which is 259.83. So now that we know that, it is easily to calculate the angle C, the interior angle at C, is going to be equal to the azimuth of CB minus azimuth of this in green of CD. And this equals to 259.83 degrees minus azimuth CD, 137.78 degrees. Let's see, 259.83, 137.78 minus, and I get 122.05 degrees. And this is the angle C. Okay, looking at the answer, it looks like B is my correct answer. You can verify in case you have something more similar. If this was 122, let's say, it would have been better. If this was 122, you might say, oh, which one is my angle? Just calculate 122 plus 3 over 60 plus 13 over 3600, and this should give you 122.05. Go ahead and check that. Okay, the correct answer is B.